Thank you everyone for joining us today. I am Molly Sarver. I am the Senior Land Use Planner at Indiana County Office of Planning and Development. I work as the Sustainability Coordinator for the Indiana County Sustainable Economic Development Task Force. And we have a summit series planned for you for the month of March and into April. If you guys have any questions throughout the presentations, feel free to comment on the live stream. We'll be watching that. You can go ahead and comment something in the question and answer feature or in chat, and we'll try to address any thoughts you have. So as I stated before, this webinar series is organized by the Indiana County Sustainable Economic Development Task Force. The task force was just started back in 2017, back in April. It started off by the Indiana County Commissioners holding a Sustainable Economy Summit, which was organized to identify opportunities for resiliency and revitalization in Indiana County. The commissioners at the time were Michael Baker, Rod Ruddick, and Shireen Hess. In September of 2017, they organized the task force, and the task force was given the responsibility of developing a report. To create that report, they engaged the community. They took an input, identified areas of concerns for the community, and they identified these 4 focuses for the task force to focus on. So the first one was sustainable agriculture, then renewable energy, building construction materials, and environmental restoration and stewardship. Within these 4 focuses, they looked for opportunities for economic development, workforce development, and citizen education. They also identified 5 executive recommendations. Oops, sorry, there we go. So the first was to create a new mission, and that was to continue their work looking for more opportunities and capitalizing on the opportunities they saw that aligned with the recommendations listed in the report. They wanted to develop an Office of Sustainability. We do not have a full Office of Sustainability, but I do operate as a sustainability coordinator, so we do have people staffed with responsibilities related to the task force. They also wanted to hold an annual Sustainable Economic Summit. This is our 4th one. We're not doing it, we usually do them in person, but given the circumstances of the times, we are doing it online. They also want to incorporate sustainability into long-range plans at the municipal and county level. And they also wanted to, expand our broadband access. So in 2018, they, put forth the report for approval by the commissioners, and they shared it with the community. They had, a bunch of speakers, and, in 2019, we did this again. We had our next sustainability summit, and it was pretty successful. Unfortunately, we weren't able to hold a sustainability summit in 2020, due to the pandemic. But, we are more than happy to, take this as an opportunity to try and do something different, do it online. So usually our webinar or our summits would be one day, and we'd have about 5 presentations. But with this summit, we are getting to do hopefully 12 different presentations. So we're getting to expand the topics we're covering. And hopefully we'll be able to reach more people since it'll be online. You can go and check out our old summit presentations and recordings by going to our website, sustainableindianacounty.org. You'll go to the top of the page, click events, and then click previous summit events, and you'll be able to see different PowerPoint presentations and also recordings from our summit that we held in 2019. If you're interested in getting more involved with this Sustainable Task Force of Indiana County, go to sustainableindianacounty@gmail.com to contact us, or visit sustainableindianacounty.org for more information about other events we hold. I put in the chat some links to our report that I mentioned, as well as links to our summit page for this summit and for our general website. If you hang on to the end of this webinar, we will automatically put you into our exit survey. You can also go online to our summit page to find an exit survey. It would be really helpful if you filled out this survey because it lets us know whether or not we are covering topics that you're interested in, and tells us what areas we can improve upon. So we would appreciate that. Our next webinar is going to be Thursday, March 11th at noon. So we'd appreciate it if you joined us for that. And without further ado, I introduce Edward Johnstonbaugh from Penn State Extension. Thank you so much for joining us today, Ed.
Thank you very much. It's a pleasure to be here, and it's a pleasure to get a chance to share this information with your audience. I'm, as Molly indicated, I'm from Penn State Extension. Oop, I'm at the back of the slideshow here. Oop. Should have ran this backwards. So here's page number 1. So today we're going to be talking about renewable natural gas with biodigesters. That may be something that members of the audience have some familiarity with, but more than likely, it's a topic that's kind of new, and but it's also a very timely topic. As we go through these slides, we'll get an opportunity to learn about changing views on anaerobic digestion and extended uses of it, opportunities that are coming down the pike. So just a little background on anaerobic digestion in general. It's a natural occurring process. It takes place whether humans are involved in it or not. And the goal of our discussion today is to talk about the actual harnessing of the process for human benefit. And there's quite an extended history of that, going back many centuries. And because it's a naturally occurring process, in our present day use of anaerobic digestion, the goal is always to have a beneficial environmental outcome. So we incorporate, or we utilize anaerobic digestion as a means of curing an issue, resolving a problem, or improving the environment. With that process, we also end up with some other benefits, some co-products, perhaps, that help to pay for the project, help to make the economics work. And economics, when we're talking about sustainability, is very important. And I want to just take a minute and touch on the use of the term sustainability. It as we move on in the 21st century here, we use this term in many different topics. Excuse me, grab a little swig here. But sustainability must make economic sense. A process to be considered sustainable has to make economic sense. It also has to benefit the environment. And it also has to have a benefit for the community in which the process is located. So in the long and the short of it, we're looking for good things. Anytime we invoke a process, design a process that we consider it and we consider to be sustainable, we're looking for 3 legs of the stool in order to meet that test. So the term anaerobic, now there's a word that we don't use necessarily in our everyday conversation, but it's very important to get this on the table as we move forward with our discussion today. But anaerobic refers to processes that take place in the absence of free oxygen. So the picture I have here is a picture of outer space where there's no oxygen. And that's what we attempt to accomplish in our anaerobic processes because the microbes that are involved in anaerobic digestion don't do well in the presence of oxygen. Strange as that may sound, we do have life forms on planet Earth that thrive in the absence of oxygen. And what we're going to be talking about is a process where we need to keep oxygen out of the picture. So the digestion process, the anaerobic digestion process, very simply drawn out here, involves a tank or a vessel that has a cover on it that we are able to push organic material into and extract organic material out of without introducing oxygen into the contained vessel. So the picture that we're looking at here, we have a means of pushing material down into the vessel from the right-hand side, and we have a entry exit means on the left-hand side where organic matter that had been in the vessel for some period of time is allowed to exit, maintaining the level at a constant height. So if we're pushing in 50 gallons of new material, we make the assumption that 50 gallons of material that's been in the digester for typically 20 days is going to exit it on the left-hand side. In the meantime, the vessel is designed with an airspace at the top where the methane gas, which is the purpose of this process to generate methane, is allowed to bubble off and accumulate. And as the pressure builds in that airspace, then the methane gas is allowed to be drawn off and used for some purpose that we'll talk about. So what kind of material are we pushing into our digester vessel? Organic material, as I said, it takes a lot of shapes and forms. I just have 4 examples here. A head of lettuce, some corn stalks. The one picture there is a waste bin at a cafeteria, for example, where people, put their food on their tray, and when they're done, they dump it into a waste bin. That's excellent source of organic material. And I also have a wheelbarrow filled with manure. And today's discussion is going to focus on manure as an organic waste stream for use in anaerobic digestion, but we're not limited to that. And I want you to, think about that as we go through the discussion, where there's different sources of organic material that go to waste or, sit on the roadside like wood chips or something like that, just composting, and which isn't a bad thing, but it doesn't produce any of the co-products that we're going to be speaking about. But the other important thing about our anaerobic digestion process is maintaining optimum operating conditions. So for a typical anaerobic digester, the range of operating temperature is between 90 and 100 degrees Fahrenheit. And it's very important to keep a healthy colony of microbes that you keep them happy, keep them growing, keep them reproducing, that we maintain a temperature ideally at about 95 degrees Fahrenheit. The other thing we need to maintain in that digester space is a proper balance of the pH, the acid versus basic balance in this system. So I have a picture of calcium carbonate. So if you've ever worked with a swimming pool, perhaps in your backyard or the neighborhood, you know that periodically, really daily, the pH is measured of the water in a swimming pool in order to keep it healthy, and to adjust the pH volumes of calcium carbonate, or if it's running acidic, we want to bring it to neutral. We would add a calcium carbonate perhaps, or if it's running basic, we would add an acid of some sort in order to keep the content of the digester in balance. And the other thing that needs to be done on a daily basis is we have to feed our digester. We have to give it a fresh supply of new organic material on a daily basis to keep it up and running, keep all those microbes happy. Because a healthy colony of microbes is what's going to do all the work for us. And remember, these guys are living in there without oxygen. So keeping them happy by maintaining a proper balance of pH and temperature is critical to maintaining the health of the digester. And as if you were involved in the operation of a digester, you become in tune with what's going in, the pH, the temperature of the system, and the production of natural gas, the production of biogas, and how they all that balance, how important that balance is to maintain, to see by observing how the digester was performing by the amount of methane gas that's being produced. So there's definitely an opportunity to get in tune with nature if you would become involved with operating an anaerobic digester. So digesters can come in many shapes and configurations, and they need to be sized appropriately for the use that they're intended. So if we were, for example, at a food processing plant where we were making potato chips, and we had an awful lot of potato peels that were coming out of that process, and other waste, cooking oil, for example, and we needed to process that material, we would know the volumes that we're dealing with because of the size of the plant that we built, and we would size a biodigester to handle the amount of outflow, the amount of organic material that was going to enter into our biodigester, and we would design accordingly. So in our picture here, we're looking at what's referred to as a continuous stirred tank side mix digester, and you see the components that I've mentioned here. We've got a method of injecting organic material from the left. We've got a heating system in the tank itself that's helping us, or is enabling us, to maintain that 95 degree Fahrenheit temperature. We've also, in this example, have a mixing device that allows us to keep the biodigester in some form of agitation. So we have the microbes well distributed through the material that's inside that digester. And we see there's a means of extracting biogas from the top and the co-products that come out the bottom. Typically, let me just address the co-product side of this. Fibrous material, plant fiber, is by and large what comes out of these plants, that these anaerobic digesters that are materials, fibers that are not typically digestible. Here's another digester configuration with a top-down mixing device. We in this example, heating the feedstock before it enters the digester, and we're extracting the biogas and the co-products out the side after what's the minimum time in containment there is about 20 days. So we want to design our system so that the organic material has a resident time in the digestive process of about 20 days. After that, as I said, it's been reduced down to plant fiber. And just another version of a digester layout. This is called a mixed flow digester or plug flow, mixed plug flow digester, where we're mixing the material, the content of the anaerobic digester in addition to keeping it heated. And then the final, probably the most simple form, is just a plug flow digester where we're keeping the content of the digester at the right temperature. We're measuring, of course, pH coming out the co-product side, and we adjust the feedstock entering on the left-hand side there to make sure we keep our pH properly adjusted and we've got the right temperature and our microbes are happy and biogas is in ample production. So that's a quick overview of what typical digesters configuration can look like, but of course they're not limited to that. All of these examples were continuous flow digesters. It's not uncommon for there to be a batch flow design, but if we're moving volumes of material, as we would be in the potato chip example, potato chip factory, or in the case of dairy farms, which we're going to look at here on the next slide, we need a continuous flow process in order to be able to manage the material flow, the feedstock flow, and also to keep that biogas production because all of them contribute to the success of the entire process, the sustainable success. So this is an Indiana County example for our residents of Indiana County. This is on a dairy farm in the county. This is a system that was designed for to handle the flow of feedstock from about 500 cows. This system produces enough methane to run the digester, and by that I mean keep it at temperature. And we'll talk about how we do that. Keep the methane digester at temperature, and also to run a generator, in this case a 90 kW generator that produces electricity. And that electricity is used under the rules, the net metering rules that exist in Pennsylvania. Although this particular location is served by a co-op where they've adopted similar rules, and they are allowed to feed electrical generation to the grid, as well as offset their purchases from the grid to minimize their electrical costs for their operation. The entire system's been up and running for about 15 years. So you can see that by that it's got some longevity. It doesn't run for 2 years, break, and sit on the shelf then. But what we see in the background here is the top of the digester, which in this case has a flexible membrane that's held up by the pressure of the methane gas in the digester. And we're going to look at how we get material into the digester and how we get natural gas or biogas out of the generator or out of the digester and to the generator. But the whole process, of course, starts off with our feedstock suppliers. And in this case, it's a dairy herd. And you can see some cows standing there in a freestall barn on a special floor. And this floor is designed to make the collection of manure and other wastes from the cows, as well as the spent bedding that the cows use to keep themselves comfortable. They're provided that to keep themselves comfortable through the day. And that floor is very important because it makes cleaning out the barn as easy as possible, but it also directs the material into a lagoon at the end of the structure. And what we're looking down into here is the outlet end of the barn that slopes into this lagoon structure. And at the end of the lagoon there, right in front of our the green piece of equipment, is a pump. And that pump is run by electricity, and it's on a timer. And periodically throughout the day, and it's not all of this kind of works like clockwork, because if you have X number of cows inside the barn there, and they're consuming water and feed, it's pretty predictable how much outflow is going to be accumulating there in the lagoon. So this pump here operates on a timer, and when it kicks on, it pumps the digested manure from the dairy farm there, from the dairy herd, through the green pipe exiting out of the top there and up to the digester vessel that we just looked at with the domed top on it, flexible top on it, membrane top. And at certain times of the day, the level of the lagoon drops, and the process just continues. You know, it's continuous throughout the day. That's one thing about this anaerobic digestion process, is that it continues 24/7, 365 days a year, in good times and bad, hot weather and cold. And you know, you keep those microbes happy, and you'll be producing biogas. Interesting also to note here that the pipe that you see to the left is the return from the outflow of the digester. So the liquids that come out of the digester after the 20-day retention period return to this same lagoon. So you know they're full of healthy, happy microbes that just came out of the digester after, and this outflow is after the fiber has been removed. And we'll see an example of what that looks like as we move on through the slides. So up there next to the gas, the vessel itself, coming out of the dome section of the digester vessel, is the natural gas supply. And these pipes are how that gas gets transferred over to the generator building. But one of the things that the system has to take into consideration is the removal of moisture from that biogas stream, because it's in a very wet environment, and as the biogas bubbles out of the content of the vessel, it's full of moisture. So this example here, the elbow that we see in the bucket shaped vessel here, is where the water coming out of the biogas gets managed. So the atmospheric pressure and the water in that container is what maintains pressure on the natural gas inside the pipe. I also want to do a brief advertisement for how beneficial PVC piping is. Without PVC piping, doing projects like this would be much more difficult. But as it is, if you have the advantage of being able to put parts together, and there's a rubber connector there in the upper left-hand corner that allows the operators to take this system apart and clean it out periodically without the ease of operating with PVC pipe. This would be a much more difficult installation. So anyways, here's our natural gas pipeline coming out of the biodigester. And on the other side, just adjacent to this, is the effluent exit. So as the pump that we saw from the freestall barn is pumping manure up into the one side of the digester, just to the left of this, the material flows in circular fashion throughout the round digester vessel, and the having spent approximately 20 days in the vessel, this is what the material looks like coming out. And it's all at the same elevation, the same height, because it's acting as a fluid in this structure. And this is just a set of paddles that kind of push a small amount of the spent effluent out of the vessel each time that these little paddles spin. And that is the into the pipe is connected to that, where the plant fiber will be extracted before it returns down to the lagoon that we talked about there once again at the end of that freestall barn. So this is the exiting effluent from the digester after its retention time. But let's take a closer look at this. You might find this very interesting. Here we are looking over the top of one of those paddles, and you can actually see the bubbles in the content of the leaving the vessel, still full of methane gas that's exiting the digester. So you can get an idea of just how much gas, and this is at the end of the line when gas production would be minimal. But you can see there's a lot of bubbles there coming out of that liquefied manure material that's now exiting the digester. From there, the material that's been through the digester for that 20-day resident time flows down to this centrifuge, where the material is spun and the liquid is removed from the content, and we end up with this bedding material, which is that plant fiber that I've been referring to. So the picture in the upper left of this slide is the material after it's been conveyed out into a storage area. See, it makes a nice little pyramid or cone-shaped pile of bedding material, where that can be uplifted by a skid steer or a front loader and taken back and start the process again as it is used for bedding for the cows. So that fiber just recycles and recycles through. It's clean. It's been sterilized and it's ready for use again. So it's a healthy recycling of material that keeps the animals happy, and eventually this all goes back through the digester process again. Of course, this material is excellent for as a soil amendment, and you can do other things with it, like press it into pots for starting plants. It's of course organic. It eventually dissolves into the soil, where through a compost process, it would actually be incorporated into the soil. So that's what that bedding material looks like. It's rather fluffy, and as I said, clean and odorless. So you might be surprised at the at how the process works there. The natural gas side of this, the biogas, as I said, it comes out of that side of the out of the dome-shaped area of the containment vessel, and here sits the diesel genset. That's a 90 kW unit. It pretty much runs 24 hours a day, and it consumes the vast majority of natural gas. But in the example that we're looking at here, there's still a need to have a flare where excess natural gas it is flared off in order to protect the membrane on the dome from excess pressure. So if you just let this thing run wild or run on its own, there's an opportunity there to create a higher pressure than the membrane is designed to hold. In order to safeguard that, there is a flare mechanism that burns off the natural gas before it is allowed to escape into the atmosphere, where it's a pretty excessive greenhouse gas in its intensity. So the system is designed to protect the release of that gas and convert it by burning it before that material escapes, that biogas. In the upper left-hand corner there, I have a picture of the three-phase electrical service that serves the farm here, but is connected to the generator building in particular. For economics, it's always preferable to connect at three-phase. If you have questions about that, I'd be happy to answer those. But that's an example of the electrical connection. And the lower left picture here is the control system. So the voltage and cycle, the frequency of the electricity that the generator produces is regulated through this control center here on the left. It's a critical piece of the entire installation to make address safety issues and power quality. So in addition to being connected to the grid, it's important to make sure that the electricity that's produced falls within conventional standards for power quality. Let's jump into a little bit of quick math here. A typical cow in an operation like this will weigh somewhere in the neighborhood of 1,400 pounds and is expected to produce about 14 gallons of waste each day. So if we're operating a sizable dairy, and the rule of thumb that I've learned through the years is that a 200 cow dairy is about the break-even point or the entry point for a biodigester system, an anaerobic digestion system. So just to give you an idea of the size of retention vessel that we need, if we've got 200 cows producing 14 gallons a day, and we need to hold that in the retention vessel for 20 days, we need somewhere in the neighborhood of 56,000 gallons. Just for perspective, a backyard pool, an in-ground pool may hold 10,000 gallons. So these retention vessels are typically round. It's a economic shape to build in, but they're also deep so that you can get the volume that you need, but also have that headroom at the top in order to be able to store your natural gas, your biogas from day to day and through times of high production and low production. Just thinking about that, operating 365 days a year and maintaining a temperature of 95 degrees Fahrenheit takes a lot of heat. And if we go back to our generator here, we see that the plumbing exiting the building there on the back is actually the coolant system that keeps the engine genset at the right temperature. That heat being dumped into the anaerobic vessel and maintaining temperature there. If that temperature gets too high, there's also a radiator type device outside that dumps heat just into the atmosphere. So the entire temperature of the system is maintained by the excess heat from the genset. Very important part of it then is to keep that genset running. If you're not doing that, you will need to operate a boiler with the biogas if you have the genset down for an extended maintenance period in order to maintain temperature in the anaerobic digester. So basic economics of the generator. If the machine is, I just picked 100 kW as a size, and it operates 80% of the time during a normal year, that would be 100 kW times 0.8 at 8,760 hours a year. And just picking a number of the price of avoided electricity or the price of credit that you would get from the local distribution company, the local electric distribution company, you see there's about a $70,000 benefit to operating that system. Because this is a renewable energy operation, you know, the feedstock here is grasses run through a cow's stomach. It qualifies for renewable energy credits. That every year would produce another $10,000 to the positive side of this operation. So just real simple numbers, back of the envelope numbers. This operation at 100 kW should produce somewhere around $80,000 worth of positive cash flow. Just to recap, recouping the whole picture that we've just looked at there, we can find our organic source of feedstock from many sources, even municipal waste from wastewater treatment plants, but animal manures, wastewater, biosolids, food waste like we discussed from cafeterias or food that is gone past its useful date in a grocery store. Even canned goods can be, have dumped out of their cans and run through a process like this, as well as other organics like fats and oils, so fryer oils, grease from other food processing operations, in addition to crop residue. We could, as I showed in one of the early slides there, corn stalks properly chopped up and liquefied can run through a process like this. And we see the outputs of this system is our biogas opportunities, which can produce electricity, can produce heat, and also be used as vehicle fuels and injected into the local distribution network as renewable natural gas. So it can be used to heat homes or businesses or process gas in industry. We can also produce bioplastics from some of the fiber materials that exit the digestion process. Of the digestate that exits the digestion process, we see we've got fertilizer options, animal bedding, of course, we've talked about. Pressed board materials can also be made. Packing and shipping materials can be produced out of that. I mentioned, using the organic digestate as horticultural products, like making these starter pots, and then taking the material directly back out onto the farm fields as a soil amendment. So as you see, there's nothing bound for the landfill by any part of this process. In fact, much of what we see on the input side here is organic materials that typically end up landfilled. So we're redirecting that material, and by processing it through this anaerobic digestion system, producing useful products and co-products, but we're also alleviating a waste stream. I'm going to end this afternoon's talk by mentioning that, of course, this was a teaser. No one's supposed to walk away from this 1 hour discussion as an expert on anaerobic digestion. But what you do know is a lot more about the ins and outs of the process, the possibilities, hopefully, that are out there. And also now you have my name and number where you can get in touch with me if I could help you in any way, shape, or form. If you're interested in pursuing more information about anaerobic digestion and the production of biogas, I have this link to the Extension website, but there's also below that a second link to a short course that's available through Extension. It takes about 2 or 3 hours to go through the entire content of the short course, and you'll learn much. You'll be exposed to a lot more than what I was able to cover in our 1 hour this afternoon. And finally, at the bottom of the page, I've got this Sea Change research link. As I mentioned at the start of the talk, that this is a very timely topic because there's today a lot of interest in renewable natural gas, which is what our biogas product is considered. And the University of Iowa is leading a extensive research project over the next 5 years that I am involved with at Penn State, along with a number of other folks from Penn State, and with the focus on developing renewable natural gas resources. So exactly what we're describing, or I described in the last hour, is the focus of this very intensive, well-funded 5-year project to develop renewable natural gas capacity in the United States. The benefit of which is that it avoids the carbon footprint that's produced by use of conventional fossil-sourced natural gas. So the biogas that we're talking about in the examples that I've described is considered carbon neutral, and it avoids, for every 1,000 cubic feet of renewable natural gas that's produced, we are avoiding the use of 1,000 cubic feet of fossil sourced natural gas. And the goal here is also to develop the resources. It's actually referred to as a grass to gas process, where we're encouraging the development of bioenergy crops in addition to conventional sources like manure, where we treat the biodigester itself as the cow's stomach and let the digestion of grasses take place in the bio or anaerobic digester vessel and produce natural gas for use in the things that we described on this slide here for electricity, heat, transportation fuels, and for renewable natural gas. So I think I've left about 5 minutes for us to answer questions. I'm going to end my portion of it there and ask that we have a chance to answer some questions.
All right, thank you, Ed, for that incredibly informative presentation. So I have some questions for you. Start with, it seems like this takes up a decent amount of space. How much acreage do you think it would take to have a municipal facility?
Well, I do work with municipal facilities, as a matter of fact, and typically there is a tank where digestion takes place in a municipal. There always is, but they're set up as aerobic digesters. So if you're looking at a typical wastewater treatment plant, it would be about the same size as the tank that you're looking at. The difference being is that the top would be closed. So I mentioned flexible coverings. You can also design rigid coverings that would go over that same tank, perhaps made from something like fiberglass that is lightweight but structural and able to hold the pressure. So the short answer though is about the size of what's there today. All that would be necessary would be conversion of the aerobic process to an anaerobic process.
In your experience, compared to usual municipal facilities, how smelly are the biodigesters?
How smelly?
Yes.
Well, one of the benefits of aerobic digestion, which includes the use of oxygen, is it reduces the odor.
Okay.
A properly designed anaerobic system, though, should not be leaking, because that's where you're losing your methane gas, and that's where the odor comes from. So if it's properly designed, it should be fairly almost odor-free as well.
Okay. So, from what you've said, it sounds like it takes up about as much space as already used for municipal facilities and smells better than them. What's a downside to biodigesters, whether used on a farm or for municipal purposes?
Well, they need attention. So you can't build it and walk away and forget about it. So as I said, you need to keep it fed every day. It can be fed in an automated fashion, but you know how machines are. The minute you think it's all up and running by itself perfectly, a fuse blows, a lightning strike occurs, or a bearing burns up, or some other mechanical failure occurs, and you've got downtime. Maintenance of the health of the microbes in the digester. I hope I spent enough time on that to emphasize how important that is, because when those things get out of balance, then you can end up with a gooey mess. So those are the downsides, is that someone involved with the operation has to understand, become an expert in chemistry and in maintenance of equipment that might not exist elsewhere on the farm.
Mhm. Okay, and I imagine for a municipality, if they wanted to switch to something like a biodigester system, they would already have to have people monitoring their facilities already. So this is just something that would be different if you were setting up this system on a farm or
Yeah,
someplace
I
that,
mean,
yeah.
there's certainly in most locations going to be permitting issues. The Department of Environmental Protection, for example, needs to be informed and issue a permit if you're operating a biodigester in the state.
Mhm.
Your local township or borough would also probably have permitting or zoning issues. But the long and the short of this is there are so many areas of the state, for example, in the um, where watersheds, sensitive watersheds exist, where the distribution of, the way we conventionally distribute manure on farm fields uh, create issues with nitrogen and phosphorus runoff. But if we're running that manure through a biodigester, as I showed there, we end up with this fibrous material that can be directly applied to farm fields because the phosphorus and nitrogen have been addressed in the anaerobic digestion process. So in the Chesapeake Bay area, for example, or the Chesapeake Bay watershed, um, adoption of anaerobic digestion has made big improvements in the reduction of nutrient runoff.
That's good. We do have a Q&A statement. Have you come across how cost effective it is to bring in feedstocks from surrounding areas in a hub and spoke model?
That's been looked at in years past. It's being looked at again in the Indiana County. The these models are always changing. So I brought up the renewable natural gas component of the financial, very simple financial analysis that I did, because there's a price premium placed on that product if you can get it into the natural gas distribution system. So while in the past the that model has been difficult to make work, it's not unfeasible that in the future, as a carbon market develops and some other incentives may be put in place, that model today would be successful. The big question to me is that does it fit the sustainability test, or does it pass the sustainability test? The reason I ask that, if I'm trucking waste manure, I'm trucking manure any distance, am I burning more diesel fuel on a daily basis than I'm producing biogas from the same amount of feedstock material that's been hauled? So this is an energy balance issue that has to be calculated, and I'm sure that there's a distance limitation where that model uh, doesn't pass the sustainability test if you have to truck that material an excessive distance.
Excellent. Thank you. All right. What are the dangers associated with biodigesters? I think that was kind of is there a potential for any kind of pressure or
Well, in this, we are dealing with natural gas. So
yes.
all the rules, the safety rules that apply to natural gas systems apply in this anaerobic digestion example. We may not be dealing with excessive pressure, but a spark, a lightning strike, improperly grounded equipment can create unsafe conditions. So I mentioned becoming an expert at chemistry to maintain the health and well-being of the microbe population, and the equipment, being able to repair equipment that you may not have had on the farm in the past. You also have to become a safety expert. So you need to learn, the proper handling and management of explosive gases.
Thank you. How widely adopted are biodigesters right now? How common are they in this area or across America?
I think in Pennsylvania, we've got about 20 in operation, typically on dairy farms, but there's a handful out there in the wastewater treatment world, and another, like at cheese plants, for example, where there's an excessive amount of byproduct that is left over from the cheese processing facility. So they're not extremely common, but there's enough of them around that the science is well understood, and there are resources like Penn State Extension where you can go for expert advice if you need to find help in design or operating fine-tuning operating issues with a biodigester. And as I said, I believe it's a growth opportunity.
Yeah. All right. Thank you. These are last two questions. Is there any potential for smaller biodigesters to be implemented on residential units?
Absolutely. The key is having enough feedstock, because you got to feed that every day. So the opportunity for community digesters where we collect we have a garbage waste stream, we have a recycling waste stream, and then we may add a organic waste stream, and that material would be hauled a short distance within a community and put in a community digester where perhaps the electricity offsets the operation of a wastewater treatment plant, for example, or municipal buildings or a firehouse or some common use opportunity. But yeah, I think that's another growth industry. If you, for example, if you had a large grocery store in a community that has organic material like produce that goes bad, that all goes into the organic waste stream for projects like that.
Okay, great. Yeah. And the last question, how popular do you think that biodigesters might become in 10 or 20 years?
Well, I've been describing what I think is a growth industry. I think as we, as the growth of renewable energy segues away from centralized large-scale generation, we're going to create a market where distributed generation resources like that 90 kW or 100 kW generator sits on a municipal microgrid, for example, where the police department and the fire department and the municipal facilities are served on a microgrid that also has its own generation resource, incorporating a anaerobic digester to produce biogas to operate that. They're going to become more of a packaged kind of product that's available on the market, and far more common and much more automated than what I've been describing in the example that I shared.
Excellent. And that seems to be a common theme with different types of renewable energy, because they can be adopted at a smaller scale. They can kind of help with aid in community resiliency whenever it comes to keeping those important essential services online whenever in cases of power
Precisely.
outages.
Yep.
So
So,
yeah.
so the, the essential services, street lighting, for example, or I'm sorry, traffic lights,
Yeah.
in an outage situation where the traffic lights are no longer functioning, and also, supply of water and wastewater treatment are two operations that you hate to have down for any extended period.
Yes. And as you said, other essential services like the police department, hospitals, those sorts of things.
Right.
So that's an exciting opportunity for like community resiliency. Well, thank you. That looks like all the questions that we have today. We really appreciate your time, Ed, and we're excited to share this content with our community.
I'm happy to be able to join you today, and thanks, and we look forward to the next opportunity we have to talk with you.
All right. Thank you, Ed. Thank you,
Take
everyone, for
care.
joining. Bye-bye.
Bye.